Hi, I'm Shrimai Prabhumoye, and today I'm going to talk about our work on focused attention improves document grounded generation. Document grounded generation task entails a context and a document relevant to this context, and the task is to generate text given this context and the document. The generated text must coherently fit the context and contain new information from the document. This is a high level view of the document grounded generation task. And to make it more concrete, I'm going to talk about two specific tasks in the next two slides. The first is Wikipedia Update Generation task. In this case, you have an existing Wikipedia article, and when new events occur in the physical world, newspaper articles are written about them. And you want to update this Wikipedia context given this news article. So here is an example of the monkey selfie copyright dispute where the initial reports suggested that the monkey took a selfie of itself, but later the news reports said that the monkey accidentally took a picture of itself, and this information was crucial for the court case. And hence the task is to generate this update given the news article as well as the Wikipedia context. To reiterate, the task is to generate text that coherently fits the Wikipedia context and contains new information from the news article. The size of this dataset is 636,000 instances. The second task is document grounded dialogue response generation task. Traditional dialogue response generation models only consider the chat history and generate a response that is most likely given the chat history. And that's why these models face the problem of hallucination. Now, to address this, here is a task where you have a chat history, and Alice and Bob in this conversation are talking about a movie, and most of the information that they use is from this Wikipedia article about this movie. And now the task is to generate a response to this chat history, given the chat history as well as the document. So Alice over here has used information from the document, which is marked in green, to respond to Bob. And so the task is to generate response that coherently fits the dialogue context and contains information from the document. The example that I presented on this slide is from CMU Document Grounded Conversations dataset, or the CMU DOG dataset. It is a dataset of human-human conversations collected over Amazon Mechanical Turk, and the size of this dataset is 130,000 instances. So this particular paper tackles the task of building good models for this task of document grounded generation. And we first present a stronger baseline for this task using pre-trained encoder-decoder model. So in pre-trained encoder-decoder model, we concatenate the tokens of the document with the tokens of the context and pass it through the pre-trained encoder-decoder, which in our case is the BART model, to generate this response. But what this task really needs us to do is to build a representation of the information in the document that is not present in the context. The information is not present in the context. And that's why we have the first type of extension, which is context-driven representation, or the coder model. The second thing this task really needs us to do is to focus on the information on the document. And that's why we have the document headed attention model, or the Doha model. Now for the coder model, we concatenate the tokens of the document with the tokens of the context and pass it through the BART encoder to get the representation HD. We then separately pass the tokens of the context through the encoder to get a representation HC. Once we have these two representations, we concatenate them and pass it through the transformer decoder to get this particular response. Now the parts that are marked in green in the document are parts of the document that we want the decoder to focus on. And the parts that are marked in green in the context are the parts of the information in the context that we don't want to see repeated in the response. So now let's look at the Doha model. In the Doha model, again, we have the same two representations, HD and HC, built exactly the same way that I described in the previous two slides. But now, instead of concatenating them, we pass them separately through the transformer decoder. Now, a traditional transformer decoder has two types of multi-headed attention. First is the self-attention, that is the attention it pays to the tokens that are generated so far in the decoding process. And the second is cross-attention, that is the attention it pays to the source side embeddings. And we introduce a third multi-headed attention, which is cross-attention document. And the goal of this multi-headed attention is to pay attention only to the information in the document. Now, the parameters that are marked in red, they pay attention specifically to the representation HD or the information in the document to generate this response. And as we see here, the parts that are marked in green are exactly the parts of the document that we wanted the model to focus on. Now, here are the results on automated metric, and we evaluate the success on the three automated metrics of Blue, Meteor, and Rouge. For the Wikipedia Update Generation task, we observe that Coder and Doha models, both of them outperform BART and the previous state of the art on this task. For the CMU dog dataset, the previous state of the art was a low resource model, which was also a pre-trained model on domain specific Reddit corpus. And yet when we move to BART, we see a huge improvement. We also see that a 19.7 Blue 4 improvement is given by the Doha model over the low resource model. And we get a 24% Blue 4 improvement over the BART model. Now, what these automated metrics really tell us is how close to the reference is the generated text. But this notion of grounding is not really evaluated through automated metric. And that's why we present the relevance human evaluation, where we ask the human judges to pick the option which contains information from the document and fits the context coherently. This is done using A/B testing on Amazon Mechanical Turk, and what we observe is that the no preference option is chosen most number of times, but both Coder and Doha outperform BART significantly on both these tasks. Since the automated metric and the human evaluation don't give us the complete picture or don't tell us anything about the quality of evaluation, we perform a manual inspection for the Wikipedia Update Generation task, and we categorize the errors in 5 categories. The first is linguistic variation, where the generation is a paraphrase of the reference and the generation is perfectly acceptable, as is shown in the example over here. But still it gets a low Rouge score of 41. A good 43% cases fall in this category, and this tells us the inadequacy of the automated metric. The second error class is partial hallucination, where the generation has captured some information from the document, but it has missed out on some information that is present in the reference, or it has hallucinated some information. 23% cases fall in this category. The third is incoherent reference, where the reference itself does not coherently fit the Wikipedia context. And this is true for Wikipedia pages that are in the form of lists, like the events that happened in 1340s or the timeline of DC Comics and so on. A good 22% cases fall in this category. But what we observe is that for 50% of these cases, the generation is actually grounded in the document and very close to the reference, as is shown in this example here. And yet, This particular generation gets a low Rugel score of 26, although it can be used as an alternate to the reference. The fourth error class is incorrect, where the generation is completely hallucinated the information, or it's not appropriate or completely incorrect. Only 7% cases fall in this category. Now, the four error classes that we have discussed so far, the reference itself is grounded in the document. And for these cases, about 85% of the time, the generation is either completely or partially grounded in the document. And hence, the fifth error class is where the reference itself is not grounded in the document. Only 5% cases fall in this category, and this is basically dataset noise that cannot be improved through modeling. Inspired by this manual inspection, we perform another human evaluation where we compare the reference itself with the generated text. And what we observe is that for both these tasks, the generated text is picked more number of times than the reference text. And this really shows the inadequacy of the automated metric, but also another issue where the sole reference is considered as the holy grail against which each generation should be compared against. And this is not right for document grounded generation tasks. Especially for dialogue response generation, where the same context can have multiple correct responses. And here is the summary of our work. Thank you.